Okay, let's continue from where we left off. I think we're on to tech questions, isn't it? So the following questions concern the population in millions of London by decade, years since 1800, population in millions. Using a calculator or computer program, find the fit best fit linear function, find the derivative, find the second derivative. Well, the second derivative is going to be 0 because a linear fit. So that's a bit weird. But anyways, calculus time. Hmm, yeah. Okay, and then it's quadratic. And then it so that, okay. And then it's going to go cubic? No. Okay. Right. Uh, we'll call this time 1, not 0. Okay, a bit weird. By decade, years since 1800. Ugh, okay, I'm gonna say that's like the end of 1800. Okay, population in millions. 0.8795, 1.040, 1.264, 1.516, 1.661, 2.000, 2.634, 3.272, 3.911, 4.422. Okay, let's make it our graph. You know what? I think it'd be easier if I highlight the data first. Um, Population versus time. Um, Years since 1800, population in millions. Okay. Okay. All right. Uh, let's move that over a bit. Okay. Oops, I have to add in my line. Come on. Why are you so slow? Um, okay. Whoops. Insert trend line. Ah, wrong button. Ah, doesn't matter. Insert trend line. Linear. Show equation. Okay, and then we'll put in also insert trend line quadratic show equation. Okay, there's the linear, there's the quadratic, and then there's the linear. So to answer the question, 167A, B, and C. Okay, 167B. The derivative is 0.0398. I won't write the full number down. This is a little bit too big. Can I edit it? I'm not sure if I can. Maybe I can. No, I can just move it around. Okay, I'll just write a few digits down. Okay, and that means the population is growing. So this is the rate of growth per year in millions. Okay. And then C, the second derivative would be 0. So the rate of change in growth per year in millions per year. Okay. Can I move this a bit without messing things up? Okay, B, C, and then okay, and then 168 now. B, C. Okay, so that the derivative here would be 2 times 0.000381856060606. So that's quite small. That's 0.0007637x plus then 0.004695. Oh, and did it? Yeah. And then the second derivative, 0.00076637. So same interpretations again. I guess one difference is that this is linear and this is constant. The quadratic, you can see, looks a better fit than the linear. Okay. Okay, another fitting question. But just before we look at that, let's just check the answers, please. Or 168. Or 169, I should say. Oops, too far. Quadratic. Where's my quadratic? There it is. 0. Okay. That one looks roughly right. It's funny, I don't know what software they're using. But it's a different fit. It's a different different coefficients. So they mustn't be using something like LibreOffice or Excel. Because my x squared coefficient and my x coefficient are both very small. compared to what they have. Oh, I'm looking at the wrong one. Okay, it's 167. Okay, 167. Okay, let's see. 167 is the linear. 0.039. Yeah, okay, now that one does fit. And then 0.42. Yeah, okay, so we're right for them. We're right. All right, let's look at the next one now. Could we just copy this? Let's see. 1, 2, 3, 4, 5. And then this is 0, -1, -2, -5, -7. Oh, -14. So I know what's happening here. There's a 0. Okay, and I should move them. Let's just move them out of the way if I can. Oh, come on. Come on, you're so slow. Time and position. Can I move you? Okay, put you here, and I'll put you here, and then this is position versus time. This is position in meters. This is time in seconds. Okay, now we're in action. Okay, now, what have we got first? Find the best list quadratic and then the best fit cubic. The derivative, explain its meaning. The second derivative, explain its meaning. Okay, well, 169 BC. Well, the first derivative is its velocity, and the second is its acceleration. So that's going to be fine. Same deal for 170. What we're missing on our graph is the cubic. Where'd you go, cubic? Where'd it go? That's the quadratic. That's the linear. I can get rid of that actually. Let's try this again. Oh, yeah, actually I didn't actually mark the show equation, did I? Okay, there it is. Oh yeah, it's a bit long, huh? Okay. So the first question is find the derivative of the position and explain its meaning, and find the second derivative. Okay, so the first one, the derivative of the quadratic, minus 0.6071 times 2. That's minus 1.2142x plus 0.5040 if we round to 4 significant figures, or we'll make it 5 significant figures. 50397. Okay. And then a derivative again, minus 1.2142. Oh, well, I shouldn't really say x, should I? I should put in like t. I think on the last page I left it as x. Okay. Okay. Right. Now, a little bit trickier. The cubic. So minus 0.1481481. So we'll go with 5 significant figures again. Times 3. That's minus 0.44454 t squared plus 0.50396. That'd be 7 then. Times 2. Okay, that's 1.0079 t minus 1.5939. And okay. And then now derivative again, 0.88908 t plus 1.0079. Okay, hopefully I have that right. Now, can I check the answer? Not for 170, but I can for 169. Okay. Um, quadratic. Quadratic minus 0.6071, good. Plus 0.43, good. Minus 0. Yep, okay, quadratic's right. Derivative minus, yep. Oh, silly me. I copied the wrong number. I was looking at the quadratic. 0.43571. Yeah, okay. I should have been a bit more careful with that. And the acceleration looks good then. Yeah, constant acceleration. Meters per second squared, put in the units actually. Okay, and just make sure I got the cubic one right. So the derivative here of the cubic one, yeah, that looks right. That looks right. Okay, I think I'm okay. All right, good. Happy enough. What's next now? The Pauling type 1 equation is described by that linear formula where x is the amount of prey available and a greater than 0 is the rate at which the predator meets the prey for consumption. Graph for a is 0.5. Determine the first derivative. Determine the second derivative. Interpret the interpretations and b and explain why it's not realistic. Okay. Okay, maybe we finish on this one because that would have us finish at the bottom of the page and just leave us with one page left, which I think we could easily finish next time. Yeah, it's kind of weird. So it's fx is defined as 0.5x. A is 0.5. So graph it. Oh, well, okay. It's going to be a straight line. The derivative, no problem. Determine the second derivative, no problem. It's going to be 0. So what's the interpretations? How do I use comments here? Is it, no, there's a quote, isn't it? So the first derivative, okay, let's think about what this means. Where x is the amount of prey available and a is the rate at which the predator meets the prey. So the first derivative was the a, the rate at which the predator, isn't that it? Yeah, meets the prey. Ah. How do you get comments in Derive? I forget. Comments. I want comments. Is it? What is it again? It's not the quote. It's not the hashtag. Is it the backtick? No. Is it quote? Yeah, okay, just regular quotes. Sorry. Right, and then the second derivative. So that's the first derivative. What about the second derivative now? That's the rate at which the rate that predators meet prey changes at. So, yeah, the rate of at which the predators meet prey changes at. Yeah, okay. And use the interpretations from being seen explain why it's not realistic. So I think the problem is that I would expect the second derivative to be negative because for a high first derivative, that would imply lots of encounters, which should result in a lower encounter rate as time goes by. That is, the brakes are being put on the encounter rate. Okay, let's see if we are okay with 171. This equation assumes that if there's more prey, the predators are able to increase consumption linearly. The assumption is unphysical because we'd expect there to be some saturation point at which there's too much prey for the predator to consume adequately. Yeah, okay. Yeah, that's true too. Or I would have thought you could say it the other way around. That, as I was thinking, you can't have a constant encounter rate. It's funny because they said, oh, the predators would get too full. Whereas I was thinking, well, the prey would get eaten out of extinction. So I don't know. I guess there's two ways to look at it. That's what I thought anyways. All right, I think that's a good place to wrap it up there for today. So thanks for watching. Any questions or problems, let me know in the comments, and I'll see you next time.